So I want to talk now about the integrals of vector-valued functions. So remember, we're calling our vector-valued function r of t, and then it has components that are functions of t, x, y, and z. Okay. So if we integrate r of t from a to b, what we're going to do, as you might have expected, is we're just going to integrate the individual components with respect to t, and then evaluate them from a to b. Now, if we're asked to find a general antiderivative, right, then what we will do is we will find this, right, the integral of r of t is capital R of t, right, within some constant vector c. So just like when we integrated a scalar function, right, or a real valued function, right, we would have that plus c at the end. Well, since when we integrate a vector function, we get a vector function, what we'll add, that constant, will be a constant vector function. Okay, and then looking at our second line here, so the integrating of r of t from a to b is equal to that capital R, so the antiderivative. Component-wise, and then we evaluate it at the top limit, the antiderivative at the top limit minus the value of the antiderivative at the lower limit. All right, so let's go ahead and practice. So evaluate the integral. So this first one, I'm going 0 to 2 t cubed I hat plus t to the fourth j hat dt. So we're going to get t to the fourth over 4 in the I hat direction plus t to the fifth over 5 in the j hat direction between 0 and 2. Okay, so we'll plug in 2 first. So 2 to the fourth is 16. So I'm going to get 16 fourths plus 2 to the fifth is 32 fifths. Oh, and that was I hat. I need to put my vectors on there. And then minus, so plugging in 0, I have 0 in the I hat direction and 0 in the j hat direction. So those aren't going to compete. Squeezing in already. So the answer here is just going to be 4 I hat plus 32 fifths j hat. And you could write that with the vectors as well, right? With the angle bracket, so 4 comma 32 fifths. Totally fine, either way. Okay, let's do our next one here. So notice this one looks like, right, I'm using my angle brackets. So if I integrate, right, 1 over u, I'm going to get, right, natural log of, go ahead and use my angle brackets and stay the same. So the natural log of u. So this next one, right, so we can think of that, we're integrating u to the negative 2 du. So that's going to be add 1, u to the negative 1 divided by the nu. So that next term will be negative 1 over u. And then finally, integrating 1 over u cubed, right, integrating u to the negative 3 du. So add 1, so that'll be u to the negative 2, divide by the nu, negative 2, so that'll be negative 1 over 2u squared. And then we're evaluating between 1 and 4. Okay, so doing 4 first, so I have the natural log of 4, comma, negative 1/4, comma, what is that going to be? So I plug in the 4, I'm going to get 16 times 2, so negative 1/32 minus, now plug in the 1, natural log of 1 is 0, negative 1 over 1 is negative 1, and negative 1 over 1, 2 times 1 squared is negative 1/2. Okay, and now we'll combine these. So now natural log 4 minus 0, so I'm going to write my answer here. So I have natural log 4, comma, negative 1/4 minus negative 1, so that'll be plus 1, so plus 3/4. And then I have negative 1/32 minus negative 1/2, so that means I have 1/2 minus 1/32. Do a little math up here. What is that? 16, so 15 30 seconds. Oh my gosh, I wish I would have used a different color. Wait, I've got a different color. Hold on, here we go. Okay, Number 3. So now my vector, so now I have 2 dimensions again. So I hat, j hat. So this first one, right, this is our inverse tangent. So just writing our antiderivative, this is the inverse tangent of t. Oh, it looks about the same color, doesn't it? The second one, I'm going to come down here. Let's just do a little working. So I'm doing t over t squared plus 1 dt. So this is going to be a u sub because I have that t in the top. So we'll let u equal t squared plus 1 so that du is 2t dt. So I've got the t. Here's the 2 and the 1/2 to balance. So this is 1/2 integrating 1 over u du. Oh, there we go. So that's going to be 1/2 natural log u. Okay, so up here, right, I'm just going to write that down. So I have now 1/2 natural log, and u is t squared plus 1. You can do absolute values, but since I'm right, t squared is all has to be positive. I'm adding 1, has to be positive. I know that my argument will be positive. So then from 0 to 4. Oh my gosh. Okay, let me find my green pen so we can actually see that. Stuff's getting too crowded in there. Okay, so evaluating at the top limit. So I have the tangent of 4, comma, 1/2 natural log 17 minus, then I'm going to plug in the 0. So I have tangent of 0 is 0. And the tangent of, so 0, I'm sorry, the natural log, plugging in a t of 0, 0 plus 1, 1. Natural log of 1 is 0, times 1/2 still 0. So that second limit is just a 0. So this is my final answer. Okay, last one before I do in my initial value problem. So finding our antiderivatives. So we'll do our u subs, right, kind of on the fly. So here's our antiderivative. So I'm going to have negative e to the negative t. I need a 2. I need a 1/2. 1/2 sine goes to negative cosine 2t between 0 and pi fourths. So plugging in the pi fourths, so I get this one, negative e to the negative pi fourths, comma, negative 1/2 cosine pi halves. Okay, and then minus what we get when we plug in the lower. So e to the 0 is 1, so be careful on that one. Zeros don't always just go away, so we'll get a negative 1 here. And then cosine of 0 is 1, so that second one is actually going to be a negative 1/2. Okay, so now let's think about it. Cosine of pi halves, actually this one is a 0. Okay, so let's go ahead and write our answer right here in this box here. So I have negative e to the negative pi fourths plus 1. Negative e to the negative pi fourths plus 1, comma, and then I have 0 minus a negative 1/2 or 1/2. Oh, that was kind of a fun answer. Okay, so that's the answer to 4. Sorry about my messiness. Okay, last one. A little bit more light here. So this is an initial value problem. So I know the first derivative and I know an initial condition. I know that the original vector r at 0 is supposed to equal 1, 1, 1. Okay. So if I want to do that, this is going to help me find that vector c. Okay, so we're going to start by finding our, right, r vector. So we're going to integrate term by term. So cosine t goes to sine t. Sine 2t, right? We just practiced that. That goes to negative 1. Okay, I practiced it. You guys just wrote it down maybe. Negative 1/2 cosine 2t. You should convince yourself that that's what it's supposed to be. Comma, and then this is going to be t squared over 2. Okay. And then I have plus that c vector. So let's just call it cx, cy, cz. Okay, and then let's find those c, x, y, and z's. So I know that when t is 0, my r vector, I want my final answer to be 1, 1, 1. Okay, so we're just going to go term by term. So sine of 0 is 0, right? Sine of 0 is 0, but I want it to be 1. that tells me that c of x is going to be 1. Okay, so now we'll check the y version, right? R of 0 for the y part, I want to be 1. So cosine of 2 times 0, cosine of 0 is 1. So right now, it is negative 1/2. So I have negative 1/2 plus what to get to 1? So I have negative 1/2 here. I need to add it to some y component here to get a final answer of 1, right? So I have to get 1/2 and then write 1 more. So this one here will be 3/2. And now we'll check z. So r of 0, I plug a 0 into my z component. I have 0 over 2. That's 0. So 0 is what I get from my antiderivative. I want it to be 1. That's going to tell me that c of z is 1. Okay. So the final vector, right here is my constant vector. My c vector is going to be 1, 3/2, 1. Sorry, get that on screen. Okay. So r equals, and now that pen's dying. Okay, so r equals, here's my final vector initial value problem. It is cosine t plus 1, sine 2t plus 3/2, t plus 1.